So if we mix 1 ml of bromine water, so that's basically bromine dissolved in water, and plus 1 ml of acetone, and then add 1 ml of HCl. Then in the beginning of a reaction, the color will be kind of a orange brown. And because the bromine is consumed over time, so that color become lighter and lighter. And eventually, when the bromine completely consumed, then the color should be gone and the solution become clear. So if we look at the absorbance over time, it should give you a curve sort of like that. So starting with relatively high and eventually goes back to 0 over time. Because this absorbance is related to the concentration of bromine, right? That's the Beer's law. So we can monitor the absorbance. And then, so if we just look at the linear part, we should be able to calculate the concentration gradient of time. Based on Beer's law, the absorbance equal to epsilon times L times C. The epsilon and L are constants. The L is the light path, that's 1 centimeter, and the epsilon value is provided on canvas. So if the rate equal to minus the concentration dt, then the rate should be equal to, if I convert the concentration to absorbance, then that's equal to the absorbance divided by epsilon L dt. Okay, so that's the relation between the rate of a reaction and the absorbance. So the absorbance data are provided on Canvas. You can use the absorbance over time data to calculate the reaction rate. Remember, we use the initial rate only. So that means we only use the linear part of the initial reaction. So how can you tell that's linear part of the reaction once you have the data? I give you absorbance versus time. If you make a plot and you get a curve looks like that, and currently the initial part here looks like linear, but can you decide, are you going to use only this part, or maybe a little more use that part? How you decide your data is linear? You want to put the data into a fit and see the R square should be larger than 0.95. Then you can assume this part is linear. If it's smaller than 0.9, that means this part is no longer linear. You need to narrow your data range to make sure only use a linear part. For this reaction, we know the reaction rate we can calculate based on the concentration or absorbance of bromine, and that's equal to reaction constant times the concentration of acetone to the order of P, and then bromine to the order of Q, and the hydrogen to the order of R, right? If we take log, natural log of both sides of the equation, so the log rate equal to log K plus P times log acetone concentration. And if we keep the bromine concentration and hydrogen concentration at a constant, then these two terms will be constant, right? So you have the reaction rate, you have the different concentration of acetone, and if you make that into a plot, a linear plot, the slope P will be your reaction order to acetone. So remember in your homework 1, question 2, that one, because number of data points is limited. There's only 2 data points. So you cannot make a linear plot, right? You need to have more than 3 data points to make a meaningful linear plot. You probably didn't do a linear plot for that one. And in our case here, you will have a more than 3 data points for each reactant. And you should be able to use the linear plot to generate the reaction order. That equation is only handout, page 623, equation number 27 to 7. When you calculate the concentration of each reactant, make sure don't forget the dilution factor. I'll show you what the dilution factor is in this slide. So this is a much larger table than the one you had in homework 1. But the essential idea is the same. So let's look at round 1, 2, 3, 4. 1 through 4. The concentration of hydrogen and acetone will be kept at a constant. We're not going to change the concentration of hydrogen and acetone. We're going to change the concentration of a bromine, reduce that from X to 1/8 of X. And then we're going to measure the rate R1 through R4, okay? And from reaction 5 to 7, we're going to keep the concentration for bromine and acetone the same, right? So we're looking at the reaction 1, 5, 6, 7. And in this case, the concentration of hydrogen changed. And then for rounds 1, 8, 9, 10, we keep the concentration of bromine and the hydrogen constant. We change the concentration for acetone. Every reactant, you have a 4 data point. When you mix the solution together, remember we mix 1 ml of bromine plus 1 ml of hydrogen plus 1 ml of acetone into the cuvette. And when you mix them together, the concentration becomes 1/3 of the original concentration. So that's the additional dilution factor. That's 1/3 when you mix 3 solutions together. And when you get the reaction rate of each reaction, then you can calculate the reaction constant